Hey there, welcome to building an awesome multi-tenant SaaS with Cosmos DB. My name is Noah, and with this presentation, I'd like to share my experience building an actual project on top of Cosmos DB in Azure. The reference to trenches in the title is related to this being an actual project done by a practitioner who has no specific insider knowledge about Cosmos DB and really has just figured things out along the way. And the reference to awesome in the title is a completely subjective thing that really serves as clickbait to get you to watch this in the first place. So now that you're here, I hope you can make your own decision around that. What are we talking about, though? Well, we're talking about something called Wally, which is my project to build a modern platform for preschools and childcare centers. If you have a small child or have knowledge around childcare, you know that there's a lot of childcare centers out there who are using outdated means, certainly according to today's standards, about how to do things like keeping track of information, sending communications to parents, billing their monthly fees, enrollment, and collecting feedback and hosting forms, all kinds of things that they need to do. And we really have technology to bring to bear, of course, now. So Wally's goal is to be that platform that a childcare center could plug in to their operations and really professionalize and really make a great experience for their customers as well as the children. The specifically goals around this are make it really flexible so that you can extend it in ways that you need to make it work for your specific situation as a customer. Make it API first so that you can integrate this thing with other things in the way we expect modern SaaS platforms to do. Make it able to be maintained and improved over time. And of course, it needs to be super reliable and super performant, so it's viewed as a trustworthy platform for schools to use and ideally very cost efficient so that it doesn't cost an arm and a leg for customers and it's a sustainable business model for the platform. So just to show you that this is not an academic exercise, this is a real app. It's almost finished, it's getting close. Let me show you what it looks like. If you were to go to wally.com, at least at the time of this recording, you would see a playground link. And if you went to create a playground, what this is doing is it's actually creating a new tenant, speaking of multi-tenancy, and a new tenant in the demo area of the app, so that in Cosmos DB we've just on the fly created a bunch of example data that we're going to use in the app. And if we came in here, what we would see is just the app itself and some example data preloaded. I won't go through everything the app does, it's quite a lot, but all of this is Cosmos DB kind of surfaced through this front-end interface. If we look at this view, we see our community of all of the people involved, which include parents and staff members and administrators at the school. All of those people are serving the students that go to the school, so this is where you can keep track of information about every student. You can see their information, you can edit it, you can record attendance, you can view the history of a student, enrollment, all of that stuff here. And so what we're looking at is basically a view of Cosmos data, and so the rest of the presentation we kind of talk about how this app came to be and how it was built on top of Cosmos and other components in Azure. So if we skip back to the presentation here, the first question that confronts us when building this, certainly the one that confronted me, was, okay, so I need to be able to support any number of customers. Hopefully a lot of customers will come to Wally over time, and we need to make sure that they're all isolated from each other and that their data is safe and they can access their own data and not get mixed up with somebody else's data. So if you look at Cosmos, you'll find that there are three, at least where I was able to see, approaches available. One is a database for every tenant, so that tenant 1 and tenant 2 have their own database account with Cosmos. And when a request comes in for either one, we really look up their database account and then we issue a query against that. I think that's pretty clear about how that would work in terms of isolating things. You really have to work pretty hard to mix up a query when you're using a unique connection string against one tenant and another. So that's pretty obvious. That would isolate our tenants. And then we have a different level down, I guess, from a database is having a single database, but having a container for every tenant. And that would be less proliferation of databases. So when a new customer signs up, we just spin up a new container inside of the database instead of a new database entirely. And we can protect throughput by making it dedicated. Or if we wanted to be more economical, we could share throughput across all of these containers. That was another way. And then there's this third way that has to do with partitioning. And in particular, leveraging the logical partitions that Cosmos creates as part of the fact that it is a horizontally scaled database that requires you to identify every item as part of a partition. And so that scenario or that model has all of the data actually kind of commingled physically, but logically it's separated if you do it in a way that divides up tenants into different partitions. So this third way is the way that I ended up pursuing. And in particular, it was done by this partitioning key strategy. Basically taking the tenant ID, every tenant, every customer has a unique ID, and then appending a type to that, which references the fact that there are a number of different entity types in the system. Here is a small sample of them, there are more. But the reason that this is useful to do is if you just use the tenant ID as your partition, you could have a tenant that had all of its data in its partition. That would do the job in terms of isolation, but we have a 20 gigabyte limit per partition. So if you had a ton of data accumulate for a given tenant, 20 gigabytes gets accumulated and then bad things happen. So the appending of an item type to make this synthetic partition key, that really helps divide up the data. So if we have 36 different types of data, we have 36 different partitions per tenant. And if that's decently distributed, then we have quite a bit of headroom in terms of storage space. We could always extend that later too. But this has worked quite well if you look at it from the perspective of how it's actually managed. We have our little smiley face requester at the top. They come in and issue a request against the API in Wally to say, hey, I want all the students for tenant 2. And so the API layer is responsible for processing that request and identifying whether this person is allowed to access tenant 2 and if they're allowed to access student data. Those are 2 levels. If so, if it can determine that, and it does this based on the request bound token, then it says, okay, I'm going to issue a query to Cosmos and I'm going to construct the partition key tenant 2 and then the type of the data that's requested so that we land in this middle partition in Cosmos. And so this is effectively dividing up our data and partitioning things such that we don't ever query without a partition key, and we don't ever query without a partition key that effectively segregates data based on tenants. So it really, I think it still does guarantee that you can segregate your data as long as the API layer does validate requests securely. You don't need to physically segregate things in databases, and you don't need to physically or logically separate them in containers either. And the rationale behind this is, in my view, this is the most minimally complex thing to do. A big thing with Wally and my principle behind building it the way I have is that it needs to be as simple and maintainable as possible. Everything that adds complexity is bad. That will add to problems with scaling it and growing it and maintaining it over time. And so accumulating more databases and more containers every time you add more customers is really against your goal there. So with this approach, you have very few containers to manage. You also, in my view, simplify your code your code doesn't need to handle different databases or different containers. It handles a single database and a single container or a few. And then it really knows exactly what it needs to do in terms of checking the paths that do queries to make sure that partition key is generated in a secure fashion from the identity of the user and what they're allowed to access. This also allows, I think this is a big advantage that's missed by trying to split database or containers, this allows cross-tenant queries. So imagine that you want to do a report for your billing, for example, and you want to quickly find out how many active students there are under all of the different customers you have in Wally. Well, you can't do that very easily if you've segregated out different containers per customer or different databases. You'd have to issue a different query for every single customer to get that. If you put everybody in the same container, in the same database, you can just have a single query that goes across all the tenants on a very selective basis, and you can get all that. So that's great. And then this is a super nice thing, in my view, is that now it doesn't cost anything to add a tenant. If you proliferate databases, you're going to have at least a minimal database charge per customer every month. If you proliferate containers, you're going to have a lesser amount, but still an amount that you pay per customer every month. And there's limits on how many containers are available, or at least that starts to become a problem at some point. So to me, this is great because you can add a tenant without thinking, okay, this has just increased my operating costs. It doesn't. And that's why we could just spin up a demo playground earlier with no thought about, is this going to cost money to the organization? It really doesn't at all. It's just more data alongside other data logically isolated. And finally, I regret this super complicated bullet point, dynamic context-aware resource governance in code. What this is an overly flowery way of saying is you can control for noisy neighbors, which is the problem of we want to make sure that one tenant that has a lot of activity doesn't suck up all the available throughputs and resources from the other tenants because it's accessing using the same database. That's definitely possible. And the main reasons that people argue for doing, that I've seen to do database or container segregation, is that you can bound that cost with every tenant so they can't be noisy and disturb their neighbors. Well, I think you can achieve the same thing. You just have to be willing to do that kind of governance in your code, in your API layer. And I call it context aware here because I think there's an advantage in that your code in your API, your code knows the context about a request. It knows what the tenant is, for example. It knows what other tenants exist. It knows the situation in terms of like how busy your system is overall. Cosmos doesn't know any of that. As far as it's concerned, it just receives a bunch of requests and it has no idea about any semantics or any meaning around whether I should allow a given request or not. Whatever it hits its limit, it just says, sorry, I'm too busy, and tells you to go away and come back later. Well, if you do this kind of thing in your API, if you implement this, then you can say, oh, well, we are busy, but our super important tenant is going to be given priority over our other not so important tenants. And we can do that sort of thing at the application level that we can't do with Cosmos. So I think overall, this has been a great way to go. What does this end up looking like with containers? Well, it's actually super simple. It almost seems too simple. We have a database, and we have really 3 containers. There's the data container, there's the audit container, and then there's a change feed container. You see here as data feed leases. I'll talk about that a little bit more later. But basically, all the data goes in data, and all the audit records, which I'll talk about more as well, those all go in audit. And then that's it. So if we need to increase throughputs for the system, we can do that on the database. If we need to back up the containers, we can do that with a few targeted backups. And it's really not a lot to keep track of. So, and then we can just mirror this for a demo. So it works out to be a pretty simple architecture for the database side, not a lot to manage, but you still achieve all those goals around isolation. So hopefully that's helpful to see how that works in terms of design decision. Let's move on to talk about another goal I had with this is to make it really extensible. So if you want to add some custom field, that you can do so. And actually, instead of just subjecting to another slide, why don't we go back and look at the app again. So if I look at Agnes here, you can see that if I try to edit, I only have a few fields available. A name, a date of birth, location, guardians, a photo. That's decent, but you need to keep track of a lot of things in a preschool. You need to keep track of things like immunizations and allergies and snack times and nap times and all kinds of other information. And this varies depending on whether you're a preschool, you're a Montessori school, you're some other kind of childcare organization, maybe you're an after-school program. Everybody might have different needs. So how do we handle those? Well, in Wally, what you can do is go in and you can create a custom field on the fly. We have our standard fields out of the box, and then if I wanted to put in a new type of data, I can choose from all these different data types, numbers, references to other things, text, times of day, dates, links. Let's just do a yes/no field that says, are you a Cosmos Ninja? And we can allow permissions on this, which is actually helpful as well. And I'll show you how this is achieved. And let's let the guardians as well edit. You can see we have an API name of Cosmos Ninja, which is a camel-cased version of this. If we save that and go back to our students view, and go back to Agnes, in theory, we just added a new field. This doesn't look great smashed into the photo, but I can now check the box and say Agnes is in fact a Cosmos Ninja, and if I save that, now I see that it's true, and if I look here on my view, I now have a column for Cosmos Ninjas, Agnes being the only one currently. But that's how it's done, and it's done dynamically. You see, we just did that as a user. We didn't need to open a support request with the Wally support team. That was just done, and it works, and it's validated and everything. So let's talk about a little more about how that actually works under the covers and how that was done. Really, this is extending a schema in a way, and we'll talk about more about what it means, schema here. But to do this, it was kind of simple once I figured out like how it's possible. It seemed pretty complicated initially, but ultimately here's how I landed, and I think this could be used in other situations too. Basically all you need to do this is you need to put a custom or like a database field for custom fields, rather a property, and let's just make this a dictionary in your code. And then you can put everything that is defined nested under there so that you don't clobber any of your existing data model. And then this is all natively in Cosmos. So if you looked at the record I just created, it's going to have something like this. Underneath custom fields, it's going to have that field I just created. It's going to have a value. Of course, this is automatically indexed in Cosmos DB, so we can query on it immediately and at good performance. So we don't have to ask a DBA to do any database migrations or define a schema, anything like that. It's all done just natively. And as far as I can tell, like, this is pretty much the least amount of information you could store to have a custom extended field for your users. And this is all it takes, a single line of code and your entity type in your data, and it works. So I think that pattern is really helpful if you want to make your data extensible. And this is like the beauty, of course, of Cosmos DB and other NoSQL databases, where the database doesn't enforce a schema, doesn't need to know about a schema. It just accepts data that's valid and saves it, and then gives it back to you. So it's up to you to decide what that data means and what its form should be. And here I'm saying schemas in a schemaless world. Basically, we're told that Cosmos DB is schemaless, which it is, but that doesn't prevent you from doing a schema. And so one of the goals with Wally, of course, is not, you don't want to make something extensible and then all of a sudden it becomes garbage data that you can't trust anymore. It needs to be trustworthy in general. And with data in particular, we need to know, in my view, that we know that data is stored exactly in the correct format, that a Boolean is a Boolean, and that a option value is a correct option value, and so on. And we can do that by just imposing our own schema over top. So this is the way I ended up going in Wally, is I just created a schema type that is stored in Cosmos actually, and here's an example of one, where we just store all the information we need to make sure that we can guarantee that data is correct when it comes in and formatted correctly when it goes out. And from Cosmos DB's perspective, it just receives an item that it stores with raw JSON. So this example, you can see we have basically the gist of it is this is an option field, and you can see the valid options available. If somebody were to send a request in and they wanted to set the value of this field, we can go and check, hey, are you providing me a valid selection? It has to be one of these values, and if it's not, then we can send back a bad request result, or we can normalize it to be the correct value. So that is a way you can do schemas. As far as I can tell, this works great. You can cache the schema in memory so that you don't have to look it up every time that it comes in, and it really does allow you to be super flexible and super fast and responsive to data schema changes on the user end, but also you can keep those guarantees of really clean and well-structured data from the system point of view. So that is schemas, and now let's talk about another aspect of this, which is real-time updating, basically streaming changes. So a lot of apps, especially legacy apps in this market of childcare kind of management, it's not really that responsive. It's kind of like the old style of you have a page that you view, and if you have somebody else somewhere else make a change, your best bet is to hit refresh. And so that just hit refresh advice becomes like a bad habit where we always just have to keep refreshing if we want to make sure that we have the latest information that we're looking at. This is not required anymore. We have the technology, in other words, to prevent this problem and this bad habit, and real-time streaming is how we do it. If I show you actually what this would look like, maybe that'll make it easier to picture. Let me open up a separate instance of this environment, and I'll go, let's see, Alexis. Let's be Alexis, and that means I'm the administrator on the left-hand side and this parent on the right. Actually, that wasn't a good choice because I don't have any students in that one. So let me try Camille. Camille has a student. Okay, so if we look at Camille, this is the parent view. The parents can check in, they can view a limited set of information, but they can see their own student. And we see Daryl is Camille's son. So if I were to go to students, and let's see Daryl here, let's say that I wanted to adjust his birth date from August 6th to August 13th, and I saved that. If you notice on the right, it's August 6th, and when I save this, it's August 13th immediately in Camille's view. So that change I just made, this is a totally different session, could be across the country, whatever, this immediately updates in the parent's view. Likewise, it should go the reverse direction if, oh, I don't have that available. If I had a thing available to edit here, there are no editable fields, then it would flow in the reverse direction. But that flows between everyone. So this is kind of how that was done, how it's achieved in the system. We basically drive this through the Cosmos DB change feed, and I think this is a great combination, a great pattern that Cosmos allows, is that if you have a user sending an update through the API that lands in Cosmos, if you are aware of the change feed publishes every single instance of the change out on its feed for you to consume. So in Wally, we have a worker that consumes this feed and looks at every change that happens and then selectively causes these to queue an event that is published out through SignalR to all of the connected clients out there that should be recipients. And of course, we can figure out who those should be dynamically based on the change. If it's a student's change, then we might see that the parent is connected and we can send it directly to the parent, and we would send it to all of the other users, staff who are connected at the same time to make sure everybody always has the latest up-to-date information. And it works super well because we can see the changes streaming out. The worker is very quickly going to see that within definitely under a second and get that into a queue through SignalR. Changes are generally propagated in, at most, like a couple seconds in practice. So this is working great, and this is done through the Cosmos DB change feed and through SignalR hosted in Azure. Let's look at some specifics around how this is implemented. In particular, I thought this was useful if you're like me and you came in and when you originally saw the change feed, you assumed or saw like all of the examples being Azure functions. Like if you're going to use the change feed, just create an Azure function that subscribes to the feed and then does stuff. And that's the way that I started doing this. And it works, but what I saw was, in my experience, there are some finicky aspects to this approach. The Azure functions, at least in my environment, maybe 30% of the time when I debug, the change feed doesn't fire right away for some reason, so I have to like restart my environment. Or in Azure, your Azure functions are subject to being recycled arbitrarily at any time, so sometimes you'll see the change feed work pretty quickly, and then sometimes it'll just randomly take, a long time. So it's like 1 second, 2 seconds, and then sometimes like 15, 30 seconds. Makes you wonder if it's even working. I prefer more consistency there, and I think the customers should have more consistency. So I eventually decided to give the change feed processor a try, which is a part of the .NET SDK. And this allows you to write your own code that consumes the change feed. And you don't have to rely on Azure functions at all. I found that if you do this in ASP.NET Core, in an I-hosted service, which is a background service that you can just start up and run in the background, that is a great way to do it. And here is literally like the skeleton of the code that you need, which is super tiny. So I just need to build a change feed processor by pointing it at a container and saying how often to pull. So I say pull every 1 second, and then I start it. And every time that a change happens, it's going to trigger this handle changes method. And this method is going to be responsible for processing each change and deciding what to do with it. In the case of Wally, what's done is we inspect every item, and as fast as we can, we decide whether or not we want to queue that onto Service Bus to be something that's consumed by others. And in particular, we do this, that we send it to a queue for eventually to get picked up through and distributed out through SignalR as an event. But that's really the only responsibility of this code, is to look at the item, decide if it cares about the type of it, and send it out to Service Bus queue. So it really could keep up with a large volume and not require a lot of resources to run. And the end result of this is it's been super consistent. It's always running as often as any ASP.NET Core web app is. Restarts once a month or whatever in Azure, but the uptime is great, performance is great, and you don't have to pay an execution cost in Azure functions every time a change happens. So to me, this has been a great change, and I would encourage you, if you're thinking like Azure functions is the only way to consume the change feed, I would say look at the change feed processor in the .NET SDK. I think it works really well, and it has some advantages. So what is the architecture? Speaking of all of this flow through the system, what does it look like? I thought I would just show kind of the general lay of the land here. And this isn't everything, but it's the major components. And you can see that Cosmos is pretty central, that it has, oops, sorry about that. And so it uses, it's used as, rather, the backplane for all of the app instances. So just to go through these very quickly, these are all Azure App Service instances, the proxy, the API auth web, worker, all of those are in an Azure App Service plan, and those are app service instances. So they're running all the time, and they're basically web apps. They're split up in order to just make them more maintainable. I generally don't go for the microservices term, but I suppose in a way they're in that spirit. Really, they're each serve their own purpose. The auth, for example, is very specific to login, so it's super locked down with regards to what it does. Very few endpoints, very few concerns. API is only concerned with doing API things. The web is only concerned with serving web stuff. So in that regard, they're separately deployable, separately maintainable, and certainly they all have their individual responsibilities, and they're all fronted by a proxy that makes them transparent to the fact that they exist. According to the person requesting, they have no idea that all of this exists behind here, which of course they shouldn't. But Cosmos DB makes that possible because all the data is stored in a common data plane, and we use that in concert with worker and service bus to basically just flow all of this data through as it changes. So it's really a dynamic system in terms of data is changing all the time. Feeds are being read, published events are being created, and data flows from all the connected apps out there. So that's a little bit of the overall architecture. And then if we zoom out a little more, as I mentioned, one of the goals as well was high availability, very reliable system. You don't want to send messages to customers saying, hey, we're going to have 3 hours of downtime tonight because we have to do maintenance. Like, my preference is you should never send such a message to anybody. And you can do this, I think, if you architect things well. And Cosmos DB is super helpful here because it has this awesome thing called multi-master replication. We can create a duplicate of that architecture I just showed you as a region, and we can just duplicate that in multiple regions. So this is actually the way it's been done. We have a West US version, for example, running one of the replicas of Cosmos DB, and we have an East US version running another replica. That replication happens transparently to us. As far as the users are concerned, they just connect to the app. They're routed to the closest one to them, so they also get the performance benefit of being nearest to their, the nearest operational data center they are using. So they're going to get super fast connectivity, and they're also going to get all of their data backed up in multiple copies in every replica that exists. And we get the ability to expand this. If Wally becomes the most popular app in the world for schools to use in every continent, it's easy to just spin up a new instance in Europe, in Asia, in Australia, and so on. So if you're in any of those places and you need to use Wally, definitely let me know. But it's possible to expand this over time and really scale it horizontally and regionally that way. All right, so that's the architecture. Very sexy and exciting, but what everybody doesn't think those terms apply to is auditing. But I'm going to talk about it anyway, because auditing, I think, is an important thing for any app to do if it's going to be, high trust. And what I mean by high trust is that I think if you're going to run a business on top of a platform, and a substantial function or part of your business on a platform, you need to be able to trust it. And there's various ways that things are trustworthy. There's security and all of that. But I think another way is just trusting the data. And when it comes to things that are changing frequently, we want a history, I think, of all of the changes that have happened to an item. And so in Wally, there's auditing that happens. Every time a change occurs, meaning something is created or updated or deleted, we audit that and save a record that you see on the right, noting who did it, what entity was changed, what the actual changes were. We save a copy of the old value and the new value, and leverage the fact that Cosmos uses an E tag natively, which essentially represents the version of an item, even though there is no versioning currently. I don't know if this will happen in the future, but there's no versioned items in Cosmos. There's only the current state. So we can't go back to an old version of an item in Cosmos, and Cosmos doesn't keep track of what changed for us, but we can put this into our code path such that every time we make a change, we know to save the relevant information to allow us to reconstruct this sequence of events. In this case, I'm keeping the old E tag and the new E tag, and that ends up forming a chain. If you can imagine a number of these events for every single time that an item changes, you could chain the E tags together, and you could chain the changes together, and you could replay from some point to a later point, replay all the changes from a certain state, and kind of really reconstruct what happened and know who did what and what changed. If you need to go back to an old version of things, you could. So that's how audit is done in Wally. And again, this is like, there's no out-of-the-box way to do this. This was kind of the way it evolved as I figured out how this could be achieved. What it ends up looking like, if we take a respite from the slides again, if we go over to a student and we look at this tab right here, we can see that the change happened 13 minutes ago, and I changed the birth date from August 6th to August 13th, as I noted before. So we can see who did that, we can see what was changed, exactly when, and as we accumulate changes, if I change the locations, for example, I would see the locations changed and what the old and new value. So we can start to see a history of everything that changed. That's helpful in a lot of ways. As an operational platform, you want to be able to do that. So definitely possible in Cosmos. If you're trying to achieve such a thing, know that there is a way to go about it. And I don't know that this is, again, the right answer for everything, but it definitely seems to work well. Another topic. What about storing things in Cosmos where a Cosmos integration doesn't exist? So this is something that I encountered and held me back for a good amount of time, which is, and I see a lot of questions on Stack Overflow and so on about, like, well, I want to use such and such library or framework, but it doesn't seem to support Cosmos DB. It only supports SQL Server, or it only supports Mongo or some other data store. And so the conclusion that you could come to, you see that and you're like, well, I guess I can't use this thing because I'm trying to use Cosmos, and so I'm stuck. What I didn't really realize, and I guess maybe I'm just was a novice before, now I know a little bit more, but a lot of these things have a store interface that you can implement. And this is speaking in .NET terms at least. And so if you have something that provides you an interface for their store, you can implement against your own Cosmos repository. And that way you don't need to take a dependency on anything that you might think you have to, like entity framework, no need for that. ASP.NET Core Identity, no need for that either. Everybody thinks that's basically the only way you can do user sessions and keep track of users in a system in ASP.NET Core. It's not true. Wally doesn't use it at all, but it does all of the things that you expect to do. It has persistent sessions. It has the ability to set claims, keep track of claims, and securely authenticate individuals against different sessions. You can revoke a session, kick somebody out of every session they're active. All of that stuff that you want can all be achieved, and you don't need to resort to these frameworks to do it. And it allows you to control the back-end storage of this stuff, so you can be very careful about caching things when possible and having your data model be well designed. So in this case, what I'm showing is, here's a user session as stored in Wally through the user session type. And the important bit of this is the auth ticket. That's an authentication ticket that comes from ASP.NET Core, and you can store this by yourself just by implementing the store. And I think I have, yeah, on this slide. So in ASP.NET Core, you can do an implementation yourself of the iTicket store interface. And basically it's a few methods about, here I'm going to give you a ticket to store, and then I'm going to ask for it back. And as long as you do that, we're cool, and you can use your own way of doing that. So in this case, we're simply taking the authentication ticket that we're handed, and we're creating a new of our own type out of it. So we store the auth ticket in a form of our own and save that to this user session repository. And then we cache it for good performance and return that key. This is all transparent to the fact of, or rather it's transparent to the framework. As far as the framework is concerned, it stores authentication tickets and it gets them back. What we have done is we've stored it in our own particular way and excluded some things that we know aren't needed, and basically allowed ourselves the flexibility of keeping track of any additional information outside of this that we want to associate with a session. So that's a way to do this, and just something I thought, if you're in my situation, you didn't really fully grok the fact that you can do this, then keep that in mind. Similar thing is true. Wally uses OpenIDICT for OpenID Connect functionality as an alternative to Identity Server. And originally, if you look at OpenIDICT, you'll see that it supports, I think, SQL Server and Mongo. You think, oh well, I guess I have to use one of those, or I have to like change my Cosmos DB to use Mongo instead. But that's also not true. What I ended up doing was just implementing the stores for OpenIDICT against my own repository, and it works great. So there's no need to resort to like shying away from Cosmos because you don't have a provided, store repository for it. Okay, and then let's talk about data modeling a little more. This is just some basic things I realized over time. When you're thinking about creating your data models, I think there really is like an increasing level of awareness and doing it better than before. I don't know if there's ever a quote-unquote right way to do it, but from what I saw, if you care about performance and you care about the cost of your system and how efficient it is, then you really do need to pay attention. For example, I didn't realize early on, and I do now, that every time you add a single property to your item, that increases the cost of it. Now, obviously, it increases the size and the storage a little bit, but more importantly, it becomes more expensive to create and to update. And so if you're doing something that is updated frequently, the more properties you proliferate on your item, the more expensive it is to do those operations. So it really behooves you, if you care about minimizing the update costs and the creation costs, to have as few properties as you can, and just to really make them as simple and straightforward and small as possible. It did occur to me, as I was making this presentation, a lot of these examples of documents in Cosmos I've showed you, or items, they basically fit on half of the slide. So I think that seems like a decent rule of thumb. If you can fit your data model, a picture of it, on the slide in PowerPoint, you're probably pretty good. That's a pretty small and efficient model. And if you can't, if it's nested super deep, or it's has 50 properties, you may want to reconsider the way you're going about things. Flatter, I think, is better, so you can see that most of these properties are just on the roots. custom fields being the one exception where it has the nested item underneath, but generally all the models that Wally has are very flat and straightforward, so they're easy to query and they're easy to understand. You can also exclude things from being indexed, which is a big help. I didn't realize that either, and then I figured it out later on. An example, if we go back to this session model, this auth ticket property being an object with all this gunk underneath it, that's a super expensive thing because every single one of these becomes a path that is indexed. So 1, 2, 3, there's like 15 different indexed things I think would come out of this if I understand it correctly. You can save a lot of the costs in updating this. If you know you're not going to query on any of this stuff, which I don't, I just excluded auth ticket from indexing, and all of a sudden my sessions, creating them, updating them are much cheaper in terms of the RU cost in Cosmos. So make sure you take notice of that, and I'll show you a trick that I used to understand when that's happening. And finally, I'll just mention there's another thing that took me a while to wrestle over in my mind about should you embed everything like NoSQL. If you listen to a lot of the advice around NoSQL, they say, oh, you shouldn't reference things anymore. We don't want to normalize data. We want to just embed everything so you can just do one query and get all the information back. An example would be, if you look at these locations that I have, what I'm doing is I'm actually just storing a location ID, which is a reference to a location record. I'm not storing the information about the location. So if I wanted to know the location name, I wouldn't be able to do it from querying this student. I would have to do two queries, one for the student, and then I would notice that it has location IDs, and then I would have to query for the locations, and then finally I'd be able to get the name that this corresponds to. And that seems like, oh man, we have to do two queries. However, if you think about the cost of storing a copy of duplicate information, if I stored the location name here instead and embedded it in here, if I ever needed to change the location's name, I would have to update it in every student record in my system, which could be thousands or more. So that becomes super expensive, and that's when systems become inflexible because they are shy of allowing changes to happen. To me, there's nothing more efficient in terms of storage space than just storing this, and then I have a single place in the system where the name of this location is defined, and that's it. So I guess the point is, don't be shy about references. You can still do them. You just need to handle in your code. Again, a lot of this is coming back to, you can do a lot of things if you're just willing to put this logic and intelligence into your API layer and treat Cosmos as just a really fast data store, which is the way I've approached it. Okay, so that's a little bit about data modeling. And I alluded to this a moment ago. One thing that I noticed happening to me as I went along and the system became more and more complicated in terms of doing more things and more types of information being stored in Cosmos and more API paths and more complicated sequences of queries happening, I sort of noticed I was losing track of all of the things that were occurring, and I didn't really have a handle on what was happening exactly and how expensive everything was, whether I was doing things well or not. And so this simple thing really, in my experience, helped a lot, which is I just put in a logging line every time I do an operation in Cosmos. So this is inside the repository class, and it just says, you did a query. Oops, sorry about that. You did a query, you got this result. It charged you 3.82 RUs or whatever. It took this long. It was for this type and this partition. Every time we see that, we can just scan down this log output, and we can notice right away, if you squint, you can see times that are redundant queries, like it definitely happened many times where I noticed I queried for something and then I literally like milliseconds later queried for it a second time. And there was a reason. The code didn't understand its previous context and so on. But you can eliminate that stuff. You wouldn't do it though if you didn't know it was happening. And especially you wouldn't know that things are more expensive than you assumed. Like that auth ticket thing we talked about with the sessions. The only reason I even looked into the indexing policy on that was because I noticed in the logs, like everything is pretty cheap, under 10 RUs for creating things most of the time. And then all of a sudden my user sessions are significantly more. I was like, why is that? And then I finally figured out, oh, you don't want that gigantic nested blob under there that's being indexed if you don't need to. So preventing RU creep, just log your RU costs. This is a custom, Cosmos doesn't do this by default. This is using serialog and using just a custom log message in my repository class to do it, but I think it's a simple thing to do that yields benefits. And I guess I'll close out on just some random performance tips. Another theme here with this project was just making it really, really fast, and that was honestly one of the main appeals of Cosmos, is just the performance, the scalability of it. And so in my mind, it would be a shame to use a system like Cosmos and then which has its native capabilities, and then not use the things you can bring to bear on the upper level or the upper layers to really make it perform well. So here are some of the things I found. Number one, use the .NET SDK, and I use ASP.NET Core. To me, this is, as far as I can understand, the fastest available, the most performant stack of ways to access. I think this is probably orders of magnitude faster. Again, I don't know this for sure, grain of salt again, but to me this is the fastest way to query. So not Entity Framework, not JavaScript or anything else, just straight up .NET on ASP.NET Core. And then this allows you to use direct TCP mode, which skips multiple round trips that happen if you use other methods. So this is definitely the fastest way. If you're going to use the .NET SDK, use that mode. And then you have the ability to use in the SDK the stream-based methods, which don't throw exceptions, and they allow you to just get handed back a stream for the result. And you are then responsible for doing the deserialization yourself, but you can use system text JSON for that, which is very performant. And you can also control the serialization very easily then. You don't have to worry about what the SDK is doing. You can do camel casing or whatever else you want to do very simply. And you can also exclude items from being written if you want to. So I think that combination of things is great as far as the SDK goes. Caching, another thing I realized over time, just because Cosmos is fast doesn't mean that you can't really abuse it by querying it more times than you need to. And you'll pay for that, honestly, because every query consumes RUs, and the whole point of the throttling or the throughput and throttling mechanisms are to make sure that you stay within your boundaries. You can save a ton if you just cache data where possible. And especially caching IDs and e-tags, I found, allows you to do really efficient reads. You can always get a 1 RU read if you have the cache ID and a small document, whereas if you never cache any IDs and you're always querying, you can't do those reads directly to an ID, which are by far the fastest way and the most efficient and least expensive way to get data out. Another lesson learned, I guess, is if you are doing an API that needs paging, like if you have 1,000 students and you need to page, or you would like to allow your consumers of the API to do a page through, get the first 100 and then get the next 100 and so on. My initial instinct was, based on previous experience with SQL Server World, was you want to do that model where you have a page number and an item count that you ask for in the API. So give me page 2, 100 items, then give me page 3, the next 100 items, so on. Cosmos doesn't really do that well. for better or worse. It didn't have that support in the SQL API at all until somewhat recently, and they added offset limit. But what I found with offset limit, and I think is still true, is that if you do it, you're basically incurring greater and greater performance penalty the further you go in the pages. So by the time you get to the last page, you're querying for every item and throwing away everything except the last bit. So the lesson learned, just use the continuation token that Cosmos provides you. Forget the notion that you are going to page by a specific amount every time. And don't just give your API consumers, like, I will hand you back the continuation token, you give it to me, and we will do this in a loop until you have got all that you want. I think if you embrace that fact, then you'll be more happy on the paging side and avoid the pain of the offset limit thing. And then finally, another thing that I evolved on over time was the use of LINQ. LINQ is very seductive in that we can just construct things that are strongly typed in code, and the queries seem to be super C-sharpy in the case of .NET anyway. And what I realized over time is you don't necessarily know what's being created as far as a query goes. And if you look at Stack Overflow, you'll see plenty of questions about, I did this thing in LINQ and it's not working right. I don't know why. And to me, there's that reason and performance in general. You should just, if you're really concerned or want to nail down the performance of your system and know exactly what it's doing, then we have in the SDK a query definition that just takes a straight up string. So if I want to select star from C where C.type is 3, that kind of thing, we could run that directly in the Data Explorer, and then we could just feed it, we could make that into a query in our code too. And to me, that's the best of both worlds, because then you know exactly what queries are being created. You only create the most minimal set that you need to do what your app needs to do. And then it never comes up like, why did LINQ not do it the way I expected? So you may be happier if you get away from LINQ a little more. And that is all that I had. So I hope this was a useful kind of potpourri of different things that I saw in this project. Definitely, if you want to reach out, my email address is right there. For any reason, if you think that something I showed is the wrong way to do it and you know the right way, I'd love to hear that. If you think it's a good way and you want to hear more about some specific, I'd probably be happy to share that too. If you have a childcare center or preschool that you want to use some new software with, then we do that too. So anyway, feel free to reach out, and I wish you the best of luck on your endeavors. Thanks.